And then, yeah, so maybe the remaining time of the lecture, I will start looking into the QuTiP. And I have uploaded some notebook there in Brightspace. This is the first one. It's downloaded from the QuTiP website. Let me see if I think I have installed QuTiP. So let's run this and see if it's working. And this, okay, this is the pie plot, numpy. Okay, this will display. So you can see from QuTiP, it import quite a few things. Q object, about basis, coherent. This is density metric, create, destroy, creation operator, annihilation operator, expectation value, box state, density metric, ME solve, QI, this is identity, sigma X, sigma Y, tensor, thermal, density metric, so the animation or matrix histogram, for distribution. Okay. Yeah, this is animation. Okay, so we won't be able to go into too much in depth because we only have a few classes left. Maybe we only have 2 more. Okay, so but you can install by doing a pip install QuTiP as I did earlier this morning. Yeah. Okay, QuTiP, I think it's quantum toolbox something with Python. Okay. Yeah, so we'll go over this. So this first is the quantum object class QOBJ. It has data type and emission. Is it emission? What's dimension? The shape. Okay, this is the image. Let me not run that again. So to create a new object, you would use this QOBJ class construct Q object and 1, 0. This Q object has dimension 2, 1, shape 2, 1. It is a column vector like this, 1, 0. You can regard this as a qubit with state 0. Okay, so you could use a list in Python as an argument to this class constructor. Get the data, and this list is used to construct a matrix representation object and other property. Okay, so this is saying you could also do other things. Well, since we are playing, so maybe let's do something else. What if we have just this? This will be a bra, right? So this is cat and that's bra. Okay, so you can ask the dimensions to 1 and shape. Okay, matrix data. So this is basically what is about the list or matrix. Okay, and what is this? And you can also have these. Is this Hermitian? It's not. The type is cat. Okay, so this is this is basically illustrated. There's a data type, the dimension, and shape. Dimensions and shape are similar, but that dimension, they say it's a composite Hilbert state space structure. And the shape is more on the matrix, the data representation. Okay, so the next is to create, this is sigma y, right? You just put a matrix like that. Okay, this is Q object with dimension 2, 2, shape 2, 2. Type with operator. Okay, data type is dense. Dimension, yes. This is sigma z operator. And then you can construct, for example, a Hamiltonian. Okay, so basically you can directly take the linear combination of these Q objects. You could also do the dagger, the conjugate emission conjugation. You can do the trace, and you can say the eigen energies. Okay, the QuTiP documentation. If you want, you can go there. So this API documentations, a lot of these, for example, this object, right? Quantum states, quantum operators, gates. This is mostly what we already have learned from the circuit, but they are more than that. They have, for example, annihilation operator, creation operator. We'll probably see that soon. Okay, let's go back here. So it says normally we do not need to create Q object instance from scratch. Using its constructor and passing its image representation. You could also use the function in QuTiP that generate some state. For example, state vector, you say I have number of Hilbert space being 2 and 1 is occupied. Okay, so this is, so I guess the convention is this is 0, 1, and 1 is occupied. And you can also, change that. 0, right? 0 occupied will be this, the occupied. So it said this is equivalent to box space n. Total number you can have is n, and you have how many particles. Okay, so this is 4, 2. You could just do the above 2, 0, 4, 2. There's a quantum object of dimension 4, 1 was one side. So this is almost the same as the shape. And this is a cat. I guess you can play around with this. For example, maybe what if we say dagger? And it does become a zebra. You get you can play with this. And you can also create a so-called coherent state with truncated Hilbert space up to 10 and alpha equal to 1. I hope you still remember what a coherent state is. I can write down the formula. Let me maybe annotate. So coherent state, if you remember, this is alpha, and if you annihilate this alpha, you actually bring down this alpha as a coefficient. And in terms of number, you have alpha raised to n, square root of n factorial, number n, and there's a normalization. I think normalization is explanation alpha square root of 2. And I think this you would truncation. Truncate this on 0. Okay, this is 10. 1, 2, 3, 4, 5. Okay, so basically you would actually up to n minus 1. Then you do this, and you normalize. You will need to probably normalize because it would be different from this. Okay, any questions? We raise this. Okay, and the next one is density matrices. Really just taking the cat and bra. So this phi 2, maybe we first do the phi 2. Display this phi 2. This is the state. Right, and this is the density matrix. Take this times the row vector. Okay. Okay. Coherent state. Here is mentioned the coherent state, but you can also write in this form. So that's the density matrix, and that's what it is. Yeah, the coherent state, the weight is getting smaller and smaller, as you see here. It's 1 over square root of n factorial and alpha raised to n. I erase that. And it's truncated up to particle number 7. And this thermal state. Okay, what is thermal state? Thermal states are a state that has n photons, right? And but you have the Boltzmann weight. This is energy for n photon state, and then divided by kT. I don't know what temperature they set. So it's diagonal. Maybe they just set it 1. Everything probably just 1. Okay. So operator, we've seen the sigma x, we are defining it on our own, but it's already built in. Sigma x, sigma y, sigma z. What about the identity? Do they have identity? Yeah, Q is it? Oh, so identity is QEYE. So maybe we need to set dimension. Yeah, this is identity. Okay, harmonic oscillator has annihilation, creation operator. This is annihilation. I hope you still remember what this is. It's a truncated version, right? A act on n is square root n and then n minus 1. So if you're doing this n m, this will be n m. So this m n minus 1. So this will be 0 to m. So this is the off-diagonal matrix, and the first index m and the other one. So this one is m is n minus 1. N minus 1. And this is what? So it's 0, 1, 1, 2, 2, 3, right? So that's the annihilation of it. Truncated. So first is 1, square root 2, square root 3, square root 4, etc. Yeah, it's done. This creation operator is basically the emission contribution. And you could also add the 2, which is proportional to the position operator in some unit of mass, etc. Frequency. This is not polyact. This is the position operator. You can also do the commutation relation, like doing operator 1, operator 2. For example, a dagger, we know it's 1 identity, right? But if you truncate it, it's almost 1 except the last one here. Okay, and the x and p, x is this a plus a dagger, p is a minus a dagger over I up to this relations group 2 to do the commutator. Supposed to be I, but you see that the last one does not because that's truncation. Okay, fully it's finite dimension, so this will work. As you can verify this, multiply them, get the identity, and then square to identity. Okay. If you had two different systems, so for example, you have a 2-level system here, and this is also another 2-level using sigma z, you can define tensor product operator. Okay. So you can define, yeah, you can define, for example, this is the state. So you have a state n1, n0, and then you tensor product of the two. N is n already defined, and okay, and here's 2, so you can just use that as a qubit. So okay, this wave function, which is first excite the first qubit, excite the second qubit, because SZ should flip the sign of the excited states on side. So if you do that, then of course it will not be the same as the original one. But the ground state does not flip. Okay, this is really just checking the Z operation on 2 qubit state. Okay, so qubit are what we already know very well, but you could actually mix the two. Still, this is still 2 qubit. So, but you could actually have these kind of gens coming Hamiltonian. So you have one object is harmonic oscillator, so you use A dagger. The other object is poly Z spin, and then you can actually have them interact, right? So for example, you annihilate a photon or a soft, and then the spin get flipped to up. So this is what this Hamiltonian describing. So you can actually have this sort of mix. In QuiZKit, of course, we cannot do that. So this QuTiP allow you to do that. Okay. Yeah, so you can also create, destroy 3, create 2, the different dimensionality. And then you also have dynamics. You can solve, for example, evolution of the Schrödinger equation. So you have sigma z, this is evolution. We're going to evolve under this Hamiltonian. You start with 2, 0 state, and then you can solve using this n e solve Hamiltonian. In your state, the time. Okay, these are the observable or something. We don't evaluate them. There's a result. Yeah, so result contain 100 states. Bring down. Then I think you can do the histogram. This is doing the histogram as a function of time. I think we're running over time, but since I started late, there were about 10 minutes, no student were here. Actually, no other student are here in person. So I'm actually sitting here alone by myself. Yeah, so this is some animation about the state evolve, right? This is cool. This animation of the state we evolve. This x, so sigma x is really rotating around the x-axis, and the state psi start from I think it start from the up and then start flipping up back and forth. This visualization is nice. And you can also do the expectation value using expect. Okay, I mean, these you probably know, at least math, you know how to do that. And this is just doing the numerics for you. And you can plot plot expectation value, sigma z. I see this up and down. It really, this animation is showing you. Yeah. And you can also evaluate sigma z's, x, sigma y, and you can plot them together. So in addition to the unitary, you could also solve dissipation. So dissipation, they will give you something called jump operator. So I don't have time, but nice thing is that you just say, okay, what is the jump operator? What's the rate? And what is the Hamiltonian without jump operator? And you can define this and you can solve it, the dynamics, how it evolve in time, and you can plot this. That's a photon number. Of course, you can also animate. This is the nice thing is you have a lot of visualization tool. Yeah, so this will be the last thing I show. You animate. This number of particle is showing that as you evolve, the occupation probability is changing. Okay, so this is my last part. Okay, any question?